directly on the front page there, and it'll be easier for you to grab the links from there. So much for trying to use technology. I mean, it's wonderful. It does work. We're technologists. We want to invite that. Okay. Okay. So we're still having YouTube technical problem. Okay. Are we ready for Bill's talk? Okay. Then let's introduce Bill and his talk, Personal Space Weather Network Database and Website Update.
Okay, thanks very much, Steve. I'm Bill Engelke, AB4EJ. I'm with the University of Alabama, and I will go pretty fast because I don't want to stand between us and lunch. But what we're going to cover today, many of you, I'm sure, are aware that there is a National Science Foundation sponsored project to develop a network of personal space weather stations. What I'm going to talk about today is the development of the website that is a database and central control system where we will collect data from this network. So about the Personal Space Weather Station network, Nathaniel mentioned about this. There are two new software-defined radios, the one inexpensive and the one that's high performance. Both radios need to be set up with a GPS disciplined oscillator. There is a database/website that University of Alabama is developing under contract with the University of Scranton to hold the collected data. And we're going to also be developing an initial set of data analysis and visualization software codes. The idea at first is to study the ionosphere via Doppler shift and WWV and other phenomena, and many other applications have been envisioned for that, but you got to start somewhere. So a status on all these things: the inexpensive SDR that Case Western Reserve is developing is designed as a final preparation. I was hoping that NAOBJ was going to be here, but to give a more detail on the status of that, but he's not here. The high-performance software-defined radio developed by TAPR, it was delayed by a couple of years due to unavailability of chips. I understand we have built some now, and they're being tested. One of our main engineers was going to give Scotty was going to give a talk on this, but due to health issues with his family, he was not able to make it. So there is also a TAPR-designed magnetometer. Those have been designed, developed, tested, and I think they are in production now and in final testing. There's supposed to be more information about that at this conference. The software for all these systems is in the testing stage, and it's all open source. The website is in beta test now, and when you look at this website, you'll see there's still some things missing, still some things that are buggy. That's why you beta test. A quick overview of the architecture. On the left, you see three possible little systems that people could develop. Starting from the top, we have a grape that has its own antenna. You can hang a magnetometer off the Raspberry Pi that controls the grape, and so that can be one little station with two instruments. Below that, you see the TangerineSDR. It has an antenna. It can be configured similarly. It runs off a Raspberry Pi for its control system, and you can hang a magnetometer off that as well. And then finally, of course, you can hang a magnetometer directly on a Raspberry Pi and upload data to the internet that way. Now, there are a couple of different places where you can send this data. There is one area set up by Dave Witten where some uploading is being done. I've also got it set up where you can upload to the central control system running at UA. I think eventually we're going to transition this server to where it runs at Scranton or some other place. Maybe we'll have it running in multiple places, but the idea is to make the data available freely to everybody. All data submitted by anybody is available to everybody. This is a view of the personal space weather station central control system. That is the website, which is up and running now. If you're familiar with the SatNOGS system, this is kind of patterned after that, where you've got a string of tabs across the top that give you your high-level functions, and below is in your front page, you've got a map that shows where the stations are, and the color of the icon indicates the station status. Red is a station that has been established but has not submitted any data or submitted a heartbeat within, I think, the last week, something like that. And then if it's orange, we've seen it within the last 3 days. If it's green, we've seen it today. So you can tell the status of the uploads going on. What you're looking at there is the current status of where we're doing beta testing. We just have a couple of beta testers, myself and one other. Now, you can take a look at all the stations. These are the stations that have so far signed up, just beta test stations. And so you can look down through these. Now, how do you use this thing? First of all, you sign up for an account on the website. They're free. Go to psws.hamsci.org, add a station and one or more instruments. If you have a magnetometer and or a grape and or a tangerine, add those on there and configure it. There's documentation on how to do that on the website. It's quite straightforward. We're just supporting the grape magnetometer and tangerine right now. We don't have tangerines to test with yet. Anyway, so once you have a station in place and an instrument on it, you configure and start an uploader, and we'll provide you with software that will do the uploads. Once uploading is in place, you'll be able to see your uploads. Each upload is called an observation. There's a couple of different things that can happen with this. What we have right now, we're finding out, is really not the ideal way to do it. I have a grape, which is not running the standard grape FLDigi software, but rather is collecting complete spectrum data 24/7, putting it into a digital RF file. So those files get huge. So downloading them can be somewhat of an issue. So as soon as we get our student team cranked up this next week, actually, we're going to add another function that allows you to pick what subportions of an observation you want to download. So the idea here is that once you have observations up there, or if you see observations from other people that you would like to download for analysis, you click on the observation that you're interested in, wait for it to download. It'll show up in your download directory, then unzip the file that you have received and do your data analysis. There is software available to allow you to do a waterfall plot for the spectrum files. Magnetometer files can be very conveniently analyzed using Excel. Let me show you an example. Okay, here is an observation I'd like to analyze. I click on it. It shows up in my download directory. I unzip it, double click on it, and then open it up into Excel, whereupon I see something like this. This nice eye chart. We don't have to go into a lot of detail on this, but suffice it to say that on the left is your time stamp, and then going across the top, you got a couple of temperatures that indicate the temperature of the downhole instrument. That's the magnetometer in the ground, and the local part of the magnetometer that is running in your shack, and two different sets of 3 magnetic variables. I'm going to pick one that is very interesting to me because I'll show you in a minute. Usually what I do is on this, I work with column I, that's the H field, that's a magnetic field, and start a new column and use an average function to make every value an average of the last 100 values in column I. That takes some of the noise and random stuff out of it. It provides a little bit easier to view plot. It acts like a sort of a low pass filter. So here, okay. That is a plot from September 1st of this year. That's the magnetometer plot. You can see there's a diurnal variation, and then also on the left is a little jog that occurred due to something going on in the geomagnetic environment. Why I like this is because when I download the comparable chart from the U.S. Geological Survey, from one of the closest professional grade magnetometers, closest one to me, Fredericksburg, Virginia. There's one that was closer to me in New Orleans, but for whatever reason that couldn't find that data, didn't seem to be there. Anyway, you see how similar it is, all the way down to these little jogs here, a little jog there. And what's exciting to me is that for an instrument that cost, I don't know, what, $100, $200 maybe, we can reproduce what the U.S. Geological Survey is doing with their very nice high-grade magnetometers. Question? Oh, okay. Is there a laser pointer up here? I don't think there is there? Anyway, I was just pointing out that the cursor doesn't show up. The similarity between the curves that we see in the all the way down to little jogs, and we've seen this before. Unusual looking little jogs. They show up very nicely in our homebrew magnetometers. Okay, here's a laser pointer. Don't let me forget to get this back to you. Yeah, just talking about comparison of this to this little jog here. Even little small stuff seems to show up very well between and something like that and that. So now spectrum data. This is coming from, I have an example of a running great system that, well, it's not running at the moment, but a system that I use at home to collect data. It uses the Grape 1 hardware running with a Raspberry Pi. However, it doesn't use FLGG. It uses GNU radio. So GNU radio is being used for signal processing of the audio data that comes off an audio chip card plugged into the Raspberry Pi, and then outputs a data file, which you can both display on the front of your screen and download it. My system, I was going to demo this, but my system developed demo-itis on the way here. I think there must have been a software update that changed something. It will start to boot and then go into a black screen, which indicates to me it's setting the video controller into a mode that my display does not support, or something along those lines. And I've tried 10 different mechanisms to try and start it up in safe mode, but none of them work. So anyway, you can look at the hardware. It's next door in the demo room. And if anybody knows how to fix that, I will buy you lunch. Anyway, so download an observation that has been uploaded. You download it to your system, unzip it, and then you can run it through some plotting software. The plotting software is something that, as I said, we're going to implement this where you can do it right on the website. But as of today, you have to download the data to your system, and it runs through a system that uses digital RF to unpack it, then it does an FFT, and then displays it using Matplotlib. So you can see this is at my station in grid Echo Mike 63 FJ, and you can see as we get close to sunrise how this 5 megahertz signal gets pushed. And look, you can even see multi-modes in this. Each mode indicates a hop. Now you can take and compare this to something like the magnetometer taken at the same time and place, and you can start asking yourself, look at how this little jog here occurs about the same time as that. Are they related? Some of these questions we don't know yet. They have to be worked out. Well, if that little jog created that, why don't we see other things here? So, this is sunrise. So it's a sort of a different thing. Well, you wouldn't expect something, a solar mass ejection to affect you when it's dark on your side of the earth. So, I mean, there's a lot to learn about this. I must confess that a lot of it is beyond my level of knowledge right now. So here is what we talked about when we talk about multiple hops. I think Nathaniel covered this in some of his talks, some of his discussion. As you get closer to sunrise, you start getting multiple hops, and what happens is each time you get a hop, it magnifies the amount of movement in the ionosphere and the amount of change in the frequency. So you can't see it very well because my plotting software leaves something to be desired. But if you look at this closely enough with the right kind of monitor, you can see 4 different hops here. You see a ground wave here, but maintains the same frequency as the WWV, and then 1, 2, 3, and up here you can't see it very well, but there's another hop in there. So that's interesting that we are seeing that kind of thing using a very low-cost device like the Grape. In my case, I'm using a loop antenna, which has a preamplifier, and another preamplifier at the shack to compensate for coax loss, and all that was designed by N8OBJ from Case Western Reserve. This is another interesting thing that you can see. This is AD0RR's data. He is a beta tester. You can see little sine wave shaped jogs in the frequency. Perhaps these are medium scale traveling ionospheric disturbances. These show up both in frequency and in amplitude. Then you can do things like this. You can compare what you're getting between different stations and see how they differ. See, you get this little jog here in both of them, but notice that it starts to be different about here. And I put this down to differences in distance. AD0RR is closer to WWV than I am, but far enough away that he does sense changes that are ionosphere derived, not just copy and straight ground wave. So this is fun to look at this and educate yourself on what's going on in the ionosphere. So what are we going to do next? We are looking for more. 5 minutes. Okay, sure. Well, we're winding up here. We are looking for more beta testers who are willing to set up a magnetometer, get it working, and then start uploading to this system, help find all the remaining bugs and missing features, of which I'm sure there are plenty. We are working on software for producing magnetometer spectrum plots on the web server to eliminate the need for downloading the data if you just want to look at a single thing. Sapnogs does this very well with their system. And we're in final preparations for producing both the Grape version 2 and the Tangerine software-defined radios. We are planning some further tweaks and cleanups for the website right now. For example, when you take a look at the size of an observation, it's just shown as bytes. And so it's a gigabytes, and you have to squint at it and manually in your mind imagine where the commas should be to figure out how big it is. We're going to clean up a lot of usability things like that. So if you would like to get involved, there's a Monday night meeting. I think Nathaniel talked about a couple of the different telcos that we have going on, but the Tangerine one is every Monday night at 9 p.m. Eastern, 8 p.m. Central, and then a Thursday afternoon telco every other week at 3 p.m. Eastern, 2 p.m. Central for science discussions. Okay, all right, stand corrected. So if you're interested in the science one, talk to Nathaniel and make sure to get the Zoom credentials to get into that. So that concludes my talk, and any questions? Okay, very good. Here's a question.
I went to PSWS.hamsci.org and got a potential security risk. Am I getting something wrong? Okay.
Yeah. This is the first time you use it, you have to accept that. Yeah, that's another one of those things that needs to be fixed. Yeah, yeah, yeah. What causes that is we have this running on the University of Alabama system, and so, but we wanted it to appear to come from HamSCI, and so your browser detects a difference between the domain name HamSCI and the domain name ua.edu, and that's what it's warning you about. So anyway, anything else? One question.
On one of the early slides, there was a indication that the downloads over a gig wouldn't work. Going forward, if the grapes and the tangerines pick up, large volume of data is probably going to be needed. Is that a limit of the current hosting site, or is that a limitation of the software that's currently implemented?
What's happening now is that the browser times out. The server's dutifully trying to zip all that, and it takes long enough that the browser detects that as a broken link to the server. What we're going to do is we're going to put a second step in where when you pick one of those big downloads, it'll come up and say, okay, what day or days do you want? And try and keep the download length to a reasonable size so the browser doesn't time out. It's something real stupid like that. I mean, this is why you beta test. So I think we're out of time. So thanks very much.
Thank you. Okay. And then check. All right. Next up, we'd like to introduce, and I'm going to work on this, Nguyen Nguyen.
Nguyen.
Okay.
It's okay.
What he says. All right. Take it away.
Yes, I gave up on that about 6 years ago. So hello everyone. My name is Nguyen. I'm currently a computer engineering and computer science student at the University of Scranton. My course is KC3 UAX. I tell my friends that I love circuit and radio, so that's why I took this test and got the license. But my friend doesn't trust me. He said I just failed for Dr. Fizel's peer pressure. Or I actually call it the superior pressure because he's not exactly my peer. So I'm going to talk to you about my progress on programming the TangerineSDR FPGA. And it's also more about me learning a lot of things from this project because I'm still very inexperienced undergrad in my opinion. So Dr. Frizzell and many other presenters have already mentioned the TangerineSDR being the high performance version of the PSWS. Beside that, it's also cost effective. It's affordable by citizen scientists, which is one of the goal of that led to the creation of HamSCI. It's also a software-defined radio, and it's very modular. I'm gonna talk about how the approach that we take support these characteristics. The heart of the TangerineSDR is the data engine. And in the middle of that is the FPGA. And I'm going to tell you what an FPGA is. Before that, let me. So these are the pictures of the different components of the TangerineSDR, which are still being tested by Scotty Cowling, which unfortunately couldn't make it to the conference. We have the RF module down here. We have the clock module, the magnetometer, Raspberry Pi hat, and this is the data engine. And that's the development kit because as Bill Engelke mentioned earlier, we had a problem with the chip supply chain, and we couldn't get the chip, so we had to rely on the development kit that we bought to develop the system to actually get something working and get some progress done instead of waiting for years of doing no work. And what the Tangerine the data engine does, this is an overview drawing by N5EG, that call sign of Tom McDermott. This is the data engine. It will receive the data from the dual antenna receiver through SPI I2C protocols. I will talk to you a little more about that later. It's also interface with the clock module to ensure that everything is synchronized. And on the clock module, there's a GPSDO, so it makes sure that yeah, it's recorded, precisely. And after that, after it processes the data using the filters, the decimation, and of the digital circuit, it would packet all of those data and then transmit it over the Ethernet port. And Tom McDermott has been working extensively on the networking programming of the data engine. And I've been mentioning the FPGA. So let me tell you what an FPGA is. An FPGA is a digital circuit integrated chip. It stands for Few Programmable Gate Array. It's called a gate array because if you look at this picture over here, this is the underlying structure of the FPGA. We have lots of configurable logic blocks. A large array of those. That's why it's called a gate array. And it's few programmable because compared to things like an Intel CPU or an AMD CPU, after it left the factory, there's no way you can reprogram the hardware. The hardware is already fixed, it's set. You can only write software for it. But an FPGA, the clients, the user, they can completely reprogram the hardware itself, and it becomes a completely different chip. And that's one of the reasons why the TangerineSDR is very high performance, because we can optimize the hardware for our specific task that introduces a very, very low latency in the system. And but the downside to this is that we lose the high level algorithm control of software. So that's when a NEOS 2 processor comes in. A NEOS 2 processor is a soft-core embedded processor, which it's called a soft-core because it's not a fixed architecture. Its structure is reprogrammable within the FPGA. It's all synthesized. So, for example, I can resize the RAM and connect the NEOS to it. So that means in the future, if you ever get a link from it that says click here to download more RAM, it is not a scam. It's legit. And it's highly flexible because, as I mentioned, you can reprogram it completely. You can also write custom instructions for it. You can adjust the cache size. You can choose different mode. You can choose a NEOS that is optimized for speed. You can choose a NEOS that optimized for resources. And of course, it's cost optimized because you are not wasting your resources. The resources that you don't need, you can allocate it to other parts of the system. And it's very portable because only with a soft-core processor, you can copy and paste a CPU from one system to another. You can't exactly do that with a traditional CPU. And the NEOS is gonna be one of the main controller of a system we call the remote system upgrade. It allows us to upgrade the system in the future. So this helps the Tangerine becomes very modular. So say in the future, we want to replace the receiver with something else. We can simply just reprogram the FPGA to support that hardware without having to call back all of those systems and reprogram it ourselves. And another advantage is that when we develop the FPGA, we have to go through this I'm not referring to writing the actual script. I'm only talking about loading the compile file into the FPGA. We have to go through this very convoluted program. But with the remote system upgrade, there's a very user-friendly UI. It's a command line interface. I believe it's being worked on by Dave Lawson right now. Uh, so you can just download a file from us and put up this UI and then just select the options and select send, and it will automatically reprogram the FPGA. And this system heavily depends on the feature that's called dual configuration in the FPGA, and I'm going to tell you what that is. A dual configuration allows the FPGA to have two completely different image. This is very different from like a Python program or a Java program. It's not just software; it specifically describes the underlying structure of this chip. It describes exactly how the low-level gates are connected to each other. And when the system boots up the FPGA will first sample a hardware pin. It's called a configuration select. So it depends on if the value is 0 or 1, it will boot into the first or the second image. We're going to call the image 0 the factory image and the image 1 the application image. So when any error occurs with the first one, the system would automatically switch over to the second one. So this also serves as a fail-safe system for our TangerineSDR. And the image 0 also has another component to it. So it is it support a remote system upgrade over UART. What it does is this is the flowchart that describes how the system works. Well, in summary, what it is that initially when you program the board with the two images, you can using the configuration select pin. If you select the factory image, there is a bootloader inside of it that connect to the UI that I mentioned earlier on a computer. And that bootloader allow you that bootloader receives the file that you will receive from us, and that bootloader will automatically reprogram all of this memory inside of FPGA for you without having to go through the program. So the next thing I want to talk about when I show you the overview of the data engine earlier, there are these interface SPI and I2C. I'm gonna mention briefly what those are. So this is the the diagram of what it is. The I2C is a hardware protocol that allows the two different hardware to talk to each other. It uses only 2 wires, so it's very simple, and you can actually add more slave to this system, and they can all share this one wire right here. And this is the message that is sent over this SDA wire. It's the important ones you need to care about is the address frame. This specify which slave we are going to talk to, and that is how we can all share just a single wire. And then there's a read or write bit which specify if we are reading data from the chip or we are sending data to the slave. And then we have the data that follow. And the next one we have is an SPI. It's a serial peripheral interface. It's also a hardware communication protocol, except it uses a lot more wires. You can see there's a clock. It's a synchronous system. So there's a clock signal. There's a master out, slave in. So this is the output on the master. On the slave, sometimes they also have a MOSI port, which means is a slave in, so is an input for a slave. And then here's master input, slave output is a similar story, except it's the reverse. And then we have chip select. So depending on which one is an active low signal, so whichever one have a receive a 0 signal, that slave is currently being selected for communication, and all the other slaves are treated as not being connected. And it's full duplex because you have separate input and output signal, so we can have reading and writing all at the same time. This system is fast. This protocol is fast, very simple, and continuous operation. That means the SPA actually doesn't require a start and a stop condition. as soon as a slave is selected, the community can start until the slave is deselected. However, the ADC that we have on the dual channel receiver is an AD9648, which is an ADC from Analog Devices, and they have their own protocol for SPI, which give us a lot of trouble because the development environment that we use for the FPGA, they have support for the general purpose SPI, but not for this very unique protocol that Analog Devices develop. Instead of using at least 4 pin clock input, output input, and chip select, it uses only 3 pin. It combine input and output into a bidirectional signal path. That means it's only half duplex now. You cannot read and write at the same time. And this SPI protocol is what allows us to configure the dual channel receiver. And down here is the message that being sent with this protocol. You can see that it's actually quite similar to I2C instead of SPI. What it does is as soon as the slave is selected, it's going to send out 16-bit instruction, with the first bit be determining if the master is trying to read or write, and then the next 2 bit determine how much data is going to be read or written, and then the following bit will determine which address of the memory register in the receiver we are going to talk to. For example, if the address is 1 and we're trying to read, the ADC would provide us with a unique identification for the chip that we're using, which is 809648. So now that I understand all of this, my job is to essentially program all this into Verilog, which is the program that the FPGA is written in. And one of the irony with programming FPGA is that I talked to you a lot about dual configuration and remote system upgrade. It was all of this came out like about a 50-page documentation, and it was very anticlimactic when I actually had to program the board, because all it took was I actually counted everything. It took me exactly 12 mouse clicks to finish the system. So I actually went through a 50-page documentation just to click on, just to click 12 times. And I'm going to talk to you a little bit more about a few difficulties that we have with the project right now. I currently have no access to the hardware. I don't have the RF module or the clock module to actually test them. So a lot of my work involved just speculation and simulation, which is very unfortunate. But just try our best, I guess. And the development environment is unfortunately also very outdated. It's called Quartus. It's currently being maintained by Intel, but it's currently like the old, that's in a family where you have like the oldest child and kind of being not the favorite child anymore. So that's the position that Quartus is in right now. It's based on Java 8, which is a very old standard for Java. The documentation on Intel's website is also very outdated. All of the information that I got for the remote system upgrade was from a documentation released in 2017. And the system, even though it's currently being updated, nobody is writing documentation for it. So a lot of it is, gotta figure everything out yourself. And the lack of support. The forum, as a software engineer, you have lots of options online. You can look up Python tutorial. There's a Stack Overflow. But with FPGA programming, you only have forum and a few Discord servers. And when you ask questions to this community, the answer tends to be, oh, very simple, you can do it. Thank you very much. yeah, so that pretty much sum up my my talk. Thank you. Any questions? Any comments? And also, because of the lack of support, we would love to welcome anyone here who knows anything about FPGA programming, Verilog programming. I'm sure Bill Engelke and Dr. Rizal already mentioned about the Tangerine SDR Telecon that we have every Monday. I will be there attending starting next Monday every week. So everyone's welcome to join.
Any questions? Well, thank you very much.